We will start with simple things in this proof, and then it will get complicated, but don't worry. So the simplest thing here to start with is to send the security parameter and the verification key. The security parameter we can easily forward. The verification key be sets as N and E that it receives, which is actually what the adversary expects. Now, when the adversary queries for a message MI, think about the following. At this point, the adversary B does not know D, so we can't generate a signature directly. But the adversary B here has the power of the random oracle. So what the adversary can do is the following. Let's pick some sigma, okay, actually let's say sigma I from Zn star. Now this sigma I is a valid signature on Mi as long as this condition holds. Now this is not part of the code, this is a thought experiment. So if the random oracle output on Mi is equal to sigma I to the power E, then this sigma I would indeed be a correct signature for Mi. Why? If the random oracle of Mi is sigma I to the power E, so here this will return sigma I to the power E, then we are supposed to compute that to the power D. Sigma I to the power E to the power D is equal to sigma I. So what we need to do is, since we have a random oracle, let's initialize a database that is empty. And then what we need to do is we need to remember in the database that if a query MI is made, the corresponding random oracle output would be sigma I to the E, and the corresponding signature would be sigma I. So we remember these, and then we can send this sigma I back. Now, let's continue our reasoning. We will fix some of these issues here. So let's say that a query Zi to the random oracle is made. Now, if this Zi is already in the database with some, let's say, Y prime, okay, and whatever is here, I don't care. So let's say this triple exists in our database where Zi is the first of this triple. Then our job is easy. We already know the corresponding random oracle output. The random oracle output Yi is indeed this Y prime. Otherwise, let's say this random oracle query has never been made. Now let's pick some Y prime randomly from Zn star. And then what we are going to do is, as usual, we are going to add to our database this triple. So Zi, its corresponding random oracle output would be Y prime to the power E, and the corresponding signature we will remember as Y prime. And then we will set Yi as Y prime to the E. So what we did here is essentially the following. We picked a random element from the group. Then we computed that to the power E. Just as we did here, if Y prime to the power E is the random oracle response, then y prime would be the corresponding signature. So we generate both the signature and the random oracle response, and we send back the random oracle response here for a random oracle query. So this is what happens from this message till this message. Now the same thing we need to do here. So we need to do this if this message is not in the database already. So if there is nothing starting with mi in the database, then we need to do this. Else, meaning here there is actually some triple that starts with mi and then something here and then sigma I here. So if this is in the database, then our job is even simpler. This sigma I response we are going to send is whatever is in the database. Consider it this way. Let's say the adversary queried for some zi, and then we generated this triple for zi, and we stored it in our database. Later on, let's say the adversary sends the same value to the signature oracle, so as a signing query. Then we already know the corresponding signature, we just need to return it to the adversary. So this is what happens in between these messages. Up to this point, there are a few important things missing. One is, everything is going well here, but remember, in a proof, our goal is to tie this outside challenge, let's say, to the inside challenge somehow, so that the output of the adversary here should help us here. At this point, we haven't used W. So if W is unused, then there's no way the adversary can help us finding X. If X to the E is not given to the adversary somehow, then the adversary has no idea about X to the E or X, so he cannot help us finding X. Now we are going to integrate this in our proof so that the adversary's forged signature will help us find X. Now we are going to do something similar to what we did in the hybrid proofs. Remember, there is no single challenge here. There are polynomially many queries that the adversary is making. In the hybrid proofs, we had polynomially many hybrids. We didn't know which one the adversary is going to distinguish, so we picked one randomly. We will do the same thing here. We are going to pick a value j randomly between 1 and, let's say, t, where t is some polynomial in the security parameter n, and this is the number of random oracle queries the adversary is going to make. Indeed, this is going to be an upper bound on the number of random oracle queries that A is going to make. So we are going to pick one of these queries as a special query. And if at this point, if we are at query number j, then we are going to do something interesting. What we are going to do is, we are going to say that the response to zj, so yj, is going to be w. Okay. So you can think of it this way. Let me use a different color. Again, this is not part of the code, but in a way of thinking, we have zj corresponding random oracle output is w, which is x to the e. Now here there should be x. Okay. We don't know x, so we can't store this. But a way of thinking is the zj has its random oracle output set as x to the e, and the signature corresponding to that would be x. So we don't know these, we don't store, but instead we return yj back as w, and we remember, so this is a value we remember, let's say as z star. We remember that particular zi as z star. We are going to use this later on. Now let's get back to answering these. So this is up to here. Answering the signature queries. Remember, we said if that message is not queried before, we generate the corresponding signature and the random oracle output. We remember these, send back this signature here. Otherwise, it's already in the database. We send back whatever is stored. Now, the problem is, if the adversary queries for a signature on Z star, remember what we said. For Z star here, we know the random oracle output, but we don't know the corresponding signature. So if the adversary sends a query mi that is indeed Z star, okay, we fail, okay? We output a failure, our simulation fails, our adversary fails. We are going to talk about this failure and the probability of it, but essentially, if that's the case, we cannot respond with a signature, we fail. Now, let's say this is not the case. Let's talk about the last part here. What happens when the adversary forges a signature? Remember, for the adversary to win, we have the following conditions. For all the MI queries, they are different from the message that is forged a signature on. And so this and this signature must verify. So verify sign using this verification key with this message output by the adversary, and the signature must accept. If these are the case, and so this is the case that the adversary A wins. If in addition to these, M is indeed equal to Z star, okay, so these are necessary for adversary A to win. This is not a condition for adversary A to win. This is an extra condition we are imposing. If all these three hold, think about the signatures here. So if M is Z star, okay, so M is this Z star, we have given the adversary X to the E as the random oracle output. So if this signature sigma verifies, then it must be X. So if this is the case, then B can say that this X is indeed sigma given by the adversary. So if we think about it, if the adversary wins, and in addition that the M here, so the blue M that the adversary forged the signature on, is indeed the Z star, then adversary B wins. So if adversary A wins and A forges a signature on Z star, adversary B wins. Now we need to think about multiple issues here. First of all, is our adversary B a polynomial time adversary? Yes. Why? There are polynomial many queries here. For each query, we do polynomial number of steps. So all these operations here can be done in polynomial time. No problem there. Is B's messaging, let's say, interface with A indistinguishable from what a real challenger would have done? So A expects a verification key that is some N and E. We are giving it. A expects a signature sigma I. We are indeed giving a signature that would verify. Okay, so A can verify this. There's no problem here. Now, for the random oracle query, there's something interesting. A expects here a random group element. So we never defined the random oracle here explicitly. But this random oracle is sometimes called a full domain hash. And the reason it's called a full domain hash is that on input some M, what it returns is some random element, let's say Y, from Zn star. So it's not going to return some random bit string of length some L, let's say, but instead it's going to return an element from the group, from some particular domain, instead of a random bit string. This is why it's called a full domain hash. So it needs to be able to randomly generate elements from this full domain Zn star. Now, the adversary expects some random element from Zn star. Let's see what we are giving to the adversary. We are picking a random element from Zn star. This is all good. But instead of giving it to the adversary, we are giving that to the power E to the adversary. Now, is this distinguishable? No, there's no problem here, because remember, RSA is a permutation. So, indeed, this and this to the power E for a random Y, this is a permutation, meaning that for each Y, we can have Y to the power E, and then this again gives us a random element from Zn star. So as long as Y prime is a random element, Y prime to the E will again be a random element, because RSA is a permutation, and this part is indistinguishable as well. Next, we are going to claim the following. If the adversary A ever manages to forge a valid signature, then he must have queried at some point for this particular M. So one of these queries must be M. That's the claim. Why? Let's assume the adversary never queries the random oracle for M. So this never happens, let's say. Remember, it's a random oracle, and the signature is generated as random oracle of this M to the power D. Essentially, the verification is done such as sigma to the E must be equal to this random oracle of M. Now think about it this way. If the adversary never queried for M, essentially this part is a completely random element from Zn star as far as the adversary is concerned. If the adversary never queried the random oracle for M, this is a random element. Now, for finding a sigma such that sigma to the E is a random element, the adversary only has negligible chance. Because this is a random element, finding a corresponding sigma, your chance is negligible. It depends on the size of Zn star, but the size of Zn star is exponential in the security parameter little n. So the chance of forging a valid signature without ever querying the random oracle on that particular message is negligible. Since that's the case, we can say that if the adversary ever manages to output a valid forgery with non-negligible probability, then he must have queried at some point for M to the random oracle. This is where our guess of J comes into play. we are guessing that the adversary will forge a signature on the message that he queried as the jade query. So we are guessing indeed Zj is equal to this M. Now, the other issue is that, let's say yes, the adversary queried for M at some point to the random oracle. Furthermore, for the adversary to output a successful forgery here, remember, this M should have never been queried to the signing oracle. So nowhere here should be M. So M must have been queried to the random oracle, otherwise the adversary can only win with negligible probability. And M must not have been queried to the signing oracle, otherwise the adversary cannot win. So let's think about it this way. If our guess of this particular J was correct, so we correctly guessed the J value such that Zj is indeed M, then let's see what happens. When the adversary queries for M, we give back W, which is x to the power e, in response. If the adversary ever manages to forge a signature on that M, we know that that signature is indeed X, so we win. So if B guessed the value of J correctly and A wins, so two conditions. If B guessed the value of J correctly and A wins, then B wins. Why? Because if B guessed the value of J correctly, Zj is indeed M. In return to its random oracle query, we return x to the e. M is never queried, so B never fails if the guess of J was correct. And then when the adversary outputs a signature sigma on M that is valid, then we know that sigma must be equal to x, so we win. So if the guess of J was correct, whenever A wins, B wins. Remember, A wins with some epsilon n probability. If that's the case and the guess of J was correct, then B would win with this probability. There are at most T queries that the adversary makes to the random oracle. At least one of them needs to be this message. Therefore, B wins with probability epsilon of n over T, at least. So if epsilon of n is non-negligible, T is polynomial, non-negligible over polynomial would be non-negligible. If the RSA assumption holds, this whole epsilon over n over T must be negligible. T is polynomial, therefore epsilon of n must be negligible. So if adversary A forges a signature with non-negligible probability, then B breaks the RSA assumption with non-negligible probability. If the RSA assumption holds, which means this probability must be negligible, then indeed epsilon n must be negligible, meaning that the scheme is indeed an unforgeable signature scheme.